let me give you an example of a use of approximation. So let's say you've got two atomic clocks. Um, so here you've got one atomic clock, here you've got another atomic clock. The thing about atomic clocks is that they can measure time very accurately. So let's just say an atomic clock can measure time correct to this many a number of decimal places. So you would sync the two clocks here. Well, in the past, scientists actually performed this experiment. They would put one, they would sync the two clocks and then put one on an aeroplane and then leave the other one on Earth. So this plane here would then take off and then fly around, and when it lands back down again, they would compare the two clocks. And it turns out that the clock on the aeroplane, well, it turns out that time on the aeroplane slows down in comparison to the clock that was on Earth. So the weird thing is, I don't really fully understand this because for some reason, when something's traveling fast, for some reason time slows down. Um, you really have to ask your physics teacher this. I don't fully understand the concept of time because for some reason, if you're traveling fast, time slows down. And again, you have to ask your science teacher. So the relationship between time on Earth, that's this atomic clock here, and the time on an aeroplane. Uh, this here is the relationship between the two. So this formula connects the two. Where v here, this v here is the velocity of the aeroplane. So that's really like the speed of the aeroplane. And c here is a constant, is the speed of light. And another question is why use the speed of light as a constant? Why not any other number? But why the speed of light? What's the obsession with the speed of light? Well, this here is something that you have to ask your physics teacher. I can't fully explain this to you. Okay. Well, anyway, this if you want to read up on it, it's really you have to look up time dilation. Um, well, well, just know that when something's traveling fast, time slows down, and the connection between the two is given by this formula here. Okay, so that's the same goes with this here. Suppose you're on Earth here, and you've got your smartphone here, and then you've got a satellite whizzing around here. So the satellite is traveling really fast all the time. Um, uh, well, when something's traveling fast, time slows down, and the time on this satellite will slow down in comparison to the time on Earth. Um, but the thing is, in order for the smartphone to communicate with the satellite, um, you need to take time into account, and again you have to ask your physics teacher this. Okay, so if you look at this formula here, so the time on Earth and the time on the satellite here, the connection between the two is given by this. Now, if you look at this formula here, so this formula here is really the same as this here. Okay, and then this you can tidy this up to this. Okay, so now look at this formula here. You see this, if you so here you've got one block. So here you've got one block multiplying with another block here. You see this block here is quite complicated, so we can actually simplify this. So you can imagine you can imagine hang on, you can imagine this block you can imagine this block here as something that we're used to. So here this is in a way 1 plus x to the power of r. In a way it is, because even though you've got a negative here, you can always push the negative into the bubble here. So this then becomes a positive. Okay. Well, anyway, looking at this here, this in a way is like 1 plus x to the power of r. Now this x here, meaning this thing here, is actually very small, because if you look at this, this is the typical speed of a satellite. So here you've got a satellite whizzing around Earth, okay, and uh, the speed of the satellite, let's just say it's given by this, and this is your speed of light, And then when you look at this thing here, okay, when you look, remember that this thing here is in a way like 1 plus x to the power of r, and this x here is actually very small, because if you look at this, the typical v is this, so that's your v. And this here is your v here, and then this c here is this c here. So when you square it, when you square the v and square the c, it becomes this, and then this then becomes this, but and then this thing here becomes this. You can see that v squared over c squared is a very small number. It's a number that's very close to 0. So when you even though there's a minus here, you can always push the minus into this thing here. Okay, so this here is really in a way plus minus 0.0000018, this number here, and then this, even though it's a minus, is still very near to 0. So we can, because this thing here is near to 0 here, we can approximate it now. We can then well, when you're here, in your mind, visualize it like this. Okay, so the minute you have this, you can actually just get this times this. That then becomes this. Okay, so here you have something that's much simpler. So the relationship between the time on Earth and the time on the satellite is this, roughly. Okay.